Hello everyone and welcome to this memory map. Today we're discussing the chapter of current electricity. Now you have learned this chapter many times in your previous years. Let's quickly revise the concepts of current electricity. The first question that you must ask yourself is, where did electricity even come from? And to answer this question, we have to go back in time to ancient Greece. Ancient Greece is where the phenomenon of static electricity was first discovered. In fact, the word electron itself comes from the Greek word amber. And the reason electron is associated with amber is because in ancient Greece, they used amber to make jewelry. And when they rubbed this amber, they saw that it could attract light pieces of objects like pieces of paper or even hair. And then they said that this amber has nothing but static charges. And this was the discovery of the phenomenon of static electricity, where they said that these objects on rubbing became possessed with static charges. And then when scientists discovered more and more experiments, they saw that these charges are not just of one type. In fact, Benjamin Franklin came along and he said that static charges were of two types. One was positive and the other was negative. But then the question was that these static charges are, like the name suggests, stationary. So how do we make these static charges flow? Which means, how do we go from static electricity to current electricity? And therefore the question was how to make these charges flow for a longer period of time. And this question was settled when Alessandro Volta came along and he discovered what is the old version of the modern day battery. And he discovered the voltaic pile, which is nothing but a battery, and therefore the problem of making charges flow for a long period of time was finally settled, and we could now possess what is known as current electricity. So we figured out a way to make charges flow for a longer period of time, and with this came the definition of the electric current. Electric current is nothing but the movement of charge, and I say that charges in motion constitute an electric current. By definition, the net flow of charge in one direction through a metallic wire is known as an electric current. Now, I want to point out that I have said the net flow of charge, which means that you could have positive and negative charges flowing in all different directions, and then what you have to do is find their algebraic sum in a particular direction, and that final net amount of charge which is flowing in one direction is what we call as the electric current. To demonstrate this, let's take a small cross-sectional area in this piece of wire and see what is the amount of charge flowing through this cross-sectional area. And you will observe that here, for example, in this case, I see two positive charges and three negative charges flowing through this cross-sectional area. So these together make up the amount of charge which is flowing through this area in unit time, and this gives me the magnitude of electric current, which means electric current is nothing but the rate of flow of charge. And from here I get the formula that I is equal to Q by T, and I get the unit ampere is equal to coulomb per second. Now once we have done this, we have to move on and ask the question, what happens to electric charges when they are placed in an electric field? It's very simple. Electric charges, when placed in an electric field, experience a force. In fact, as you can see, I have applied an electric field to this piece of wire. And now the positive charges inside this wire are feeling a force towards the negative terminal, and the negative charges are going to feel a force towards the positive terminal. And more importantly, if they are free to move, they will actually move towards these opposite terminals. Now, what does this mean? It means that the current, which is nothing but the motion of these charges, actually depends upon the freedom of movement of charge. Because they are free to move, they constitute an electric current. If they were not free to move, then there would be lesser current in that case. And therefore, how much electric current is produced is directly related to how free are the charges to move. And why is this concept important? It is important because in materials like conductors, which are made up of metallic materials, the charges which flow are only electrons. This is because the positive charges are the positive ions which are fixed in one place, and therefore the current is only constituted of electrons, and therefore instead of saying that flow of charge, we say flow of electrons in case of solid conductors, which are usually made up of metallic materials. Now once you understood this, we can ask the question, what exactly is the total amount of charge flowing through a solid conductor? Then, because only electrons flow in conductors, the total amount of charge is nothing but the total amount of charge of the electrons. And therefore, that is nothing but the number of electrons multiplied by the charge on a single electron, which is 1.67 to 10 raised to minus 19 coulomb. And therefore, the total amount of charge flowing through a conductor is the total amount of charge of the electrons given by N into E. So we get the formula Q is equal to N into E. Now, finally, let us also remember that even though in conductors electrons flow, there are other materials like electrolytes in which you have the flow of both types of charges, that is positive as well as negative charges can move in materials like electrolytic solutions. And therefore, in those cases, we will have a positive charge and a negative charge both contributing to the electric current. Finally, I also want to point out that all the situations that we will come across in this chapter are those situations in which there are solid conductors, which means the situations we will talk about are those in which the negatively charged electrons are moving and the positively charged ions are fixed in place. So we say this is a situation of negatively charged electrons in the background of the fixed positive ions. Now, arguably the most famous relationship between voltage, current and resistance is the Ohm's law. Now, you must have learned Ohm's law many times in the past. Let's quickly take a look at an example which will help us develop a qualitative understanding of Ohm's law. You can see that in this example, you have two water tanks placed at different heights. It is obvious that the tank which is at a greater height will be able to deliver water faster to the container at the ground, because the greater height means that the speed of the water will be faster. However, if you take a look at the pipe which is delivering this water, then in the first case, the cross-sectional area of this pipe is much smaller than the cross-sectional area of the pipe in the second case. And therefore, this will hinder the movement of water, and therefore this will reduce the flow of water in the first case as compared to the second case. So overall, we will observe that the amount of water reaching the container per unit time is exactly the same in both cases. The first tank had the advantage of a greater height, but the second tank had the advantage of having a greater cross-sectional area of the pipe. This is actually an analogy of Ohm's law. In this case, the height of the tanks represents the voltage of the circuit. The cross-sectional area of the pipe represents the opposite of resistance, because greater the cross-sectional area, less is the resistance offered to the flow of water. And therefore, obviously, water itself is the charge flowing, and the amount of water reaching the container is nothing but the current. And therefore, this shows us that the flow of charge is nothing but a consequence of potential difference, and it explains the relationship between current, voltage and resistance by saying that greater the voltage and lesser the resistance, the greater is the current. Now, to mathematically express Ohm's law, we say that imagine you have a conductor through which a current I is flowing, and V is the potential difference between the ends of the conductor. In such a case, we write Ohm's law as simply V is directly proportional to I. That is, voltage or potential difference is directly proportional to the current. Now, from this, I remove the proportionality sign and get a constant of proportionality, which is exactly what we need, that is the resistance of the conductor, or simply put, it is electrical resistance. Now, electrical resistance is a property of the conductor by virtue of which it opposes the flow of electric current in the circuit, which means greater the electrical resistance, lesser is the flow of current in a circuit. The property of electric current is such that it is dependent not only on the material of the conductor, but also on the dimensions of the conductor itself. Now, one of the important things that resistance depends upon is the temperature. Greater the temperature, more will be the resistance, because more will be the movement of the particles inside the conductor, and these collisions give rise to resistance. And therefore, I say that resistance R is directly proportional to temperature T. Now, resistance also depends on the dimensions, like I said, and we can directly relate resistance to the length of the conductor, and we see that resistance is directly proportional to length, and I say that R is directly proportional to L. To demonstrate this, let's take a look at a conductor. In this conductor, as you can see, we have a potential difference of V between its two ends. We have a current I flowing through the conductor, and we know that there is a resistance R that this conductor possesses. We also know the length of the conductor is L. Now, by definition of Ohm's law, I can find the value of the resistance of this conductor, and it will simply be R is equal to V by I. However, what happens if I double the length of this conductor? To double the length of this conductor, what I do is I take two such conductors. Both these conductors have the exact same length, and they both have a potential difference V between their ends, and they have a cross-sectional area of A. Now, what I do is I join these conductors, and therefore I make a conductor which is double in length. I have changed no other property of the conductor. Now all I have done is double the length, and I ask the question, what has happened to the resistance? So let's quickly take a look what has happened to it. First of all, let me say that now the total length is L plus L, which is 2L. We also see that the current remains the same, that is, now the same current is flowing through twice the length of the conductor, but the value of the current is I. It is the same current I flowing through this longer conductor. However, the potential difference between the ends of the conductor is now doubled, because there was a potential difference of V between the two ends of the first conductor and a potential difference of V between the two ends of the second conductor. Together now there is a potential difference of 2V between the ends of this longer conductor. Now I'm going to calculate the resistance using Ohm's law. The new resistance will be the new voltage between the ends of the conductor, which is 2V, divided by the current of this new conductor, which is still I. And from here it is very easy to see that the new resistance, which is 2V by I, is nothing but 2 times V by I, which is 2 times the old resistance. So what did we learn? We basically learned that doubling the length doubled the resistance, and this proves what I'm trying to say, that resistance is directly proportional to the length of the conductor. Let's see if we can reach a similar conclusion in terms of the dependence of resistance on the area of cross section. Now, the resistance of a conductor is inversely proportional to its area of cross section. To see this, we have the same conductor as before. Now, this conductor has a length L and area of cross section A, as we have already seen. What I want to prove is that R is inversely proportional to this area of cross section, which means that if I reduce the area of cross section, my resistance should increase. To do this, what I do is I cut this conductor in half, and I get two pieces of this conductor, each of which has an area of cross section exactly half of the original conductor. However, as you can see, the length of the conductor has not changed. It is still L, but the area of cross section has become exactly half, which means that the current flowing through each of these conductors will also split, because now they are two pieces connected in parallel. And therefore, the current I, which was originally flowing through the conductor, is now divided into I by 2 flowing through the first piece and I by 2 flowing through the second piece. And we already know that the area of cross sections have already become halved. So now I say, what happened to the resistance? The resistance in the original case, as we already know, was R is equal to V by I. In the new case, what happens is that the resistance is equal to the new voltage, which is simply V as before, because the ends of the conductor has not changed. The same 2 points remain as were there in the original conductor. So the new resistance is nothing but V divided by the new current flowing through each of these pieces. Now this new piece has a current flowing through it which is equal to I by 2, and this gives me that R dash is equal to 2V by I again, which is nothing but 2R, which is nothing but double of the original resistance. And therefore I have proved that when I reduce the area of cross section, that is when I halve the area of cross section, the resistance doubled, and this is exactly what I mean by inverse proportionality. So I have proved that resistance is inversely proportional to the area of cross section of a conductor. Finally, I can also talk about the VI characteristics of a conductor. The VI characteristics are nothing but the relationships between the voltage and the current. But we just saw the relationship between voltage and current, which is Ohm's law. So why are we still discussing VI characteristics? VI characteristics is a representation of Ohm's law on a graph. In fact, not all materials obey Ohm's law. Materials that obey Ohm's law are known as ohmic materials, and for these materials, the relationship between V and I is linear because of Ohm's law. And therefore, if you draw the VI characteristics of ohmic materials, for example, metallic conductors, you will see that the VI characteristic is nothing but a straight line. And obviously from this graph you can tell that the slope of this graph will give you the resistance, which is nothing but tan theta is equal to V by I, which is equal to R. We also saw that resistance depends upon temperature. So what if you draw the same graph at a higher temperature? If you draw the same graph at a higher temperature, you will see that it will have a greater slope. And therefore in this case, the line 1 represents the resistance at a higher temperature as compared to line 2, because line 1 has a greater slope. And therefore I say that tan theta 1 is greater than tan theta 2, which is slope 1 is greater than slope 2, which means I can find that resistance 1 must be greater than resistance 2, and therefore the temperature of the first graph is greater than the temperature of the second graph, because I know that resistance increases with temperature. Finally, I can also see that the VI characteristics for materials which are not ohmic, for example, non-linear substances for which Ohm's law cannot be valid, will not be straight lines. They will be irregular curves. This, for example, is the graph of the VI characteristics of a diode. You can also see what the VI characteristics look like for a semiconductor. So as you can see, these materials which do not follow Ohm's law are known as non-linear substances or non-ohmic substances, and for them the VI characteristics do not come out to be a straight line. From the understanding of the relationship between resistance and length and resistance and area of cross-section, we can find what is known as the specific resistance. We already saw that resistance is directly proportional to length and inversely proportional to area of cross-section. Using these proportionalities, I can get the formula R is equal to rho L by A, where rho is the constant of proportionality between these relationships. This constant of proportionality, rho, is what is known as the resistivity of the substance. Now, the resistivity of a substance depends only on the material of the conductor and not on its dimensions. And therefore, Ohm's law can also be written as V is equal to I rho L by A. And this equation, which is just another way of writing Ohm's law, is what we will call as equation 1. We will now also define what is known as current density. Current density is nothing but the current passing per unit area of a conductor. And this area of cross-section is taken normal to the flow of current. And so we say that current per unit area taken normal to the flow of current is what is known as current density. From this comes the formula of current density, which is denoted by J, that J is equal to I by A, and we will call this equation 2. We will also now try to write down an equation for the potential difference of voltage V for a conductor in terms of the field. And this equation actually comes from electrostatics. We have learnt that if E is the magnitude of the field of a conductor, and this field is a uniform electric field inside the conductor, and if the length of the conductor is L, then the potential difference V between the ends of the conductor can be written as V is equal to E into L. And this equation, which we got from electrostatics, will we call as equation 3. Using these three equations, we can find the relationship between the current density J, the field E, and the resistivity rho of a conductor. And we get that E is equal to J into rho. We can also write this as J is equal to sigma into E. And what exactly is this sigma? Sigma is nothing but the reciprocal of resistivity, that is 1 upon rho, and sigma is known as conductivity. So we got a relationship between resistivity, the current density, and the field. This relationship, that E is equal to J rho or J is equal to sigma E, is also another way of writing Ohm's law, and so we say that this form is equivalent to Ohm's law. The next thing that I want to talk about is what is known as the drift velocity of electrons. Now we know that when no electric field is present, the electrons will move about in the conductor. As these electrons move, they suffer collisions with the heavy fixed ions of the conductor. And after these collisions, they emerge with the same speed. And we say they emerge with the same speed because we assume that these collisions are elastic, and we can assume this because the size of the fixed positive ion is much bigger than the size of the electron. And because of this, we say that the electrons emerge with the same speed after collision. However, the direction with which they emerge after collision is completely random. And therefore, on an average, the direction of all of these electrons will be equal to 0. And so we say that the electrons without an electric field will have no net velocity. And therefore, I say that average velocity is 0 because the directions are random. However, what will happen if I apply an electric field to the conductor? In such a case, I know that electrons start to move in a fixed particular direction. So I say that when an electric field is present, electrons are moving with an average velocity, because now the direction is not random, they have an average velocity overall. And this average velocity is independent of time. Now keep in mind that each of these electrons will be moving with a different velocity. Some will be slow, some will be fast, In fact, at different points in time and different regions of the conductor, the same electron will have different speeds. So I'm not saying that the electrons have a constant velocity. In fact, the electrons are always accelerating. What I'm saying is that overall, if we average the velocities of all the electrons, we will get a number which is the average velocity, which is what will be the constant that we can use. And this average velocity is nothing but what we call as the drift velocity of the electrons in a conductor. This drift velocity is denoted by V with a subscript d, d standing for drift velocity. So this drift velocity Vd is nothing but the average velocity of the electrons when electric field is present. And the formula for this drift velocity comes out to be Vd is equal to small e, capital E, tau by m. Here Vd is the drift velocity, that is the average of all velocities taken at a given instant of time. Small e is the charge on an electron. Capital E is the field inside the conductor. Tau is the relaxation time. We will learn about this shortly. And small m is the mass of an electron. So what is the relaxation time that we have used in the formula for drift velocity? Relaxation time is nothing but the average of the time between successive collisions for all the electrons. Now, even though an electric field is present inside the conductor, the electrons are moving in a fixed direction, but that doesn't mean that they are not going to undergo collisions. They are still undergoing collisions. And the time between two collisions will not be the same for each electron. The time between two collisions for one electron, that is, the time between the first collision and the second collision for one electron, is not going to be the same as the time taken for another electron between two collisions. But if we find the time taken between collisions for all of these electrons and average them all out, then the time that we get is known as the relaxation time, and therefore I say that the relaxation time is the average of the time between collisions for all the electrons in the conductor. Now finally, what I want to find is the relationship between the drift velocity, the resistivity and the current density inside the conductor. To do this, I have to first ask the question, what is the distance traveled by an electron inside the conductor in a given unit of time? We already know that the electrons are moving with a drift velocity given by Vd. If I want to find out what is the distance traveled by this electron in time delta t, all I have to do is multiply this speed, that is the drift velocity, into delta t, because we know that distance is equal to speed into time. So the distance traveled by the free electron in delta t is given by Vd into delta t. That's great. But how much volume of the conductor is an electron actually covering when it is moving in delta t time? To see this, all we have to do is multiply this distance with the area of cross section. So what I do is multiply Vd delta t with the area of cross section A, and this gives me the volume of the conductor covered in time delta t by an electron. How did we get this volume? Simply by multiplying the distance, which was nothing but the length of that portion, into the area of cross section of the conductor. So this gave me the volume of the conductor covered by the electron in time delta t. This is A Vd delta t. Once we have this, I ask the question, what are the number of free electrons moving within this volume? All I have to do is multiply the expression that I have found above by n. Why? Because n is the number of electrons per unit volume in the conductor. If I multiply this by the volume of this portion, I will get the total number of electrons inside this volume. So the number of electrons inside this volume is NAVD into delta t. Once I have this, I next ask what is the amount of charge in this volume. Okay, so I have the number of free electrons. How do I find the charge? Simply by multiplying this expression by the charge on each electron. If I have the number of electrons and I multiply it by the charge on the electron, I get the total charge. And therefore, delta Q comes out to be NAVD delta T into E, where E is the charge on each electron. Finally, now that I have the total amount of charge passing through this area in time delta T, I will simply find the current by dividing it by unit time delta T. And therefore, I get I is equal to delta Q by delta T, which is equal to NAVD into E. So the current passing through this volume is NAVD into E. Now, I already know that Ohm's law says that V is equal to IR, But instead of this I will now write down the expression that I have just obtained, and therefore I get that V is equal to NAVD into E multiplied by the resistance R. I will also substitute the resistance with its other formula, that is R is equal to rho L by A. This will give me V is equal to NAVDE into rho L by A. I cancel the areas of cross section, and therefore I get V is equal to NVDE rho L. From here I get the formula for drift velocity, that is Vd is equal to V upon Ne rho L. Keep in mind that Vd is the drift velocity, whereas capital V is the potential difference between the ends of the conductor. Finally, now I will replace this capital V with the formula that we got from electrostatics. Instead of capital V, I will write it as E into L. The LL will get cancelled, and then I will replace E by rho with the current density J, and this will give me the relationship between drift velocity, resistivity and current density that I want, that is Vd is equal to J upon Ne. The final quantity associated with the drift velocity of electrons that I want to define is known as the mobility of electrons. By definition, mobility is nothing but the drift velocity per unit electric field, which means that the formula for mobility comes out to be Vd divided by E, and substituting the formula for drift velocity which we know, we will get that mobility mu is equal to E tau by m, where tau is nothing but the relaxation time, which is the average time between collisions for all the electrons. Now, from the formula, I can see that we have only taken the magnitude of drift velocity, which means that mobility is always a positive quantity. But of course, we want to ask the question, what exactly is the significance of this mobility at all? Why do I need to define a quantity known as mobility? And the answer to this is that the drift velocity which we had defined before actually varies with field, which means that the drift velocity is proportional to the electric field. And this constant of proportionality between the drift velocity and the electric field is what is known as mobility. And because mobility is a constant of proportionality, it does not change with field, and therefore, by looking at the mobility, we can find out whether or not electrons will be able to move easily inside a conductor or not. So I'm actually saying that mobility is a constant that depends only on the substance and gives us information about the ease with which electrons move. So if you want to ask, will it be easy for electrons to move in a particular conductor, you don't look at their drift velocity because that will change with field, but you actually look at their mobility, which is a constant depending only on the material of the conductor. Now, we have already defined what is known as the resistance of a conductor, and we have said that resistance is defined as the opposition to the flow of current offered by the conductor. But sometimes we need to increase or decrease the resistance in a circuit externally. And why would we need to do that? This is because from Ohm's law we have learned that we can actually manipulate the values of current by changing the values of resistance. And therefore, in order to control the current flowing through the various materials in a circuit, we actually make use of the Ohm's law and change the values of resistance externally. To do this, we can add what are known as resistors to the circuit. These resistors, which are commercially available, are of two major types. The first one is the wire-bound resistor, and the second one is the carbon resistor. In a wire-bound resistor, the material is basically such that it is mostly insensitive to temperature. For example, alloys such as manganese, constantan, nichrome, etc. are all materials which are comparatively insensitive to temperature, and therefore these resistors can be used for experiments. However, the values of these resistors are really low, ranging from a fraction of an ohm to a few hundred ohms. And therefore you can see that we cannot use them for higher values. To do that, we have to use the other type of resistors, which are the carbon resistors. These resistors have a higher range and are made mostly from carbon. Carbon resistors are compact, inexpensive, and used heavily in all sorts of electronic circuits. The construction of such a carbon resistor consists of two connecting leads, between which is deposited a carbon substrate. This carbon substrate is then covered in a carbon composition, and over which a carbon film is deposited. Finally, this whole structure is covered in an insulating cover. And on this insulating cover is a color code which tells us the value of these resistors. Now, the resistor then made from carbon with a suitable binding material molded in the shape of a cylinder is then what is known as a carbon resistor. This resistor is encased in a plastic or ceramic jacket, which is the insulating cover. Now, because carbon resistors are really small in size, they are given a color code so that we can find the value of these resistors. In this color code, the first band, which we will call as A, gives us the first significant figure, the second band gives us the second significant figure, the third band is used as a multiplier, and the fourth band, which is D, is known as tolerance. These bands have significant meaning, and we will see how using these bands we can find the values of the resistance of the resistor. These coaxial colored rings will tell us what is the final value of the resistor by using a color coding table. As you can see, the meaning of each band is given in the table. Each color has a value associated with it. Let's say we want to find the value of the resistance of the given resistor. We first take a look at its first band A, which we call as the first significant figure, and we notice that the color of the first band is red. And therefore, in the row for the figure, we find the color red and note down its value, which we can see is 2. We repeat the same procedure for the second band B. The second band B is blue, and therefore inside the row for the figure we find the blue color and note down the number given. In this case it is 6. This then becomes the first 2 digits of the value of the resistance, that is 26. We still need to find one more digit, that is the multiplier. The multiplier in this case is of the color green, and therefore in the multiplier row we find the green color and write down the value of the multiplier, that is 10 raised to 5. And hence we get the value of the resistance, that is 26 into 10 raised to 5. Finally, the last band, that is the tolerance band, gives us the tolerance level of the resistor, which can be found by finding the silver color in the tolerance table. As you can see, the value of the tolerance comes out to be 10%. However, sometimes this last band is absent, and in such a case, this indicates a tolerance of 20%. As mentioned earlier, we need the use of resistors to manipulate the current in a circuit. And to do this, we sometimes have to form combinations of these resistors. One such combination is the series combination. In a series combination, resistors are joined only on one end. And we say that two resistors like the one shown, R1 and R2, are said to be in series if one of their endpoints is joined. Let's try to find what is the effective total resistance when I join these two resistors in series. To do that, we study them inside a circuit. Now it is very clear that since they are not connected between the same 2 points, the potential difference between the ends of each of these resistors will be different. The potential difference for the first resistor is said to be V1 and for the second one is said to be V2. However, since they are connected in series, the same current I flows through each of them. What I want to find is the total effective resistance offered by both these resistors together. From the animation itself, you can guess that having two resistors is actually making it harder for the current to flow. The final effective resistance, which I will call as R equivalent, is given by R1 plus R2, which means that two resistors when connected in series act like one resistor which is of the value R1 plus R2, and therefore in general I can say that for a series combination of n different resistors, the equivalent resistance Req is given by simply adding these resistances together. And now finally I want to comment that overall when you connect resistors in series, you increase the resistance and hence the current in the circuit is decreased. There is one other way in which resistors can be joined to manipulate the current in a circuit, and that is known as a parallel connection. Two resistors R1 and R2 are said to be parallelly connected if both their ends are connected together. You can see this is clearly different from the case of the series combination. Now I want to find what is the effective total resistance offered by this combination in a circuit. It is seen very clearly that since both the ends of the resistors are joined together, the potential difference between each of them will be exactly the same. And so I say that the potential difference between R1 and R2 is exactly the same. However, the current will now be split up on reaching the point where the resistors are joined, and therefore the current is not the same for resistors in parallel. The effective combination of a parallel combination of resistors gives us the effective or equivalent resistance using the formula that the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistances. In general, for n such resistors, I say that 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 and so on and so forth. Overall, I will say now that connecting resistors in parallel reduces the resistance and therefore it increases the flow of current in a circuit, and hence when you want to increase the current in a circuit, you connect resistors in parallel. However, when you want to decrease the current in the circuit, you connect the resistors in series. Now, we've already commented on the temperature dependence of resistance earlier in this video. We said that for metallic conductors, temperature and resistance are directly proportional, that is, resistance increases with temperature. This is because inside a metallic conductor, as the temperature increases, the ions and atoms vibrate with greater amplitudes and frequencies, causing greater collisions. If the number of collisions is increasing, this means that the time taken between two successive collisions is decreasing. So what exactly I'm trying to say is that the relaxation time is decreasing. Therefore, I say that an increase in temperature decreases the average relaxation time and thus increases resistance. But how does a decrease in the relaxation time increase resistance? This is because resistance is given by the formula R is equal to m upon Ne square tau into L by A. Here you can clearly see that resistance and relaxation time are inversely proportional. And we just saw that an increase in temperature decreases relaxation time. And if relaxation time decreases, then the overall resistance of the conductor increases. In this formula, m is the mass of the electron, L is the length of the conductor, N is the number density of electrons, that is the volume density of electrons, E is the charge of an electron, tau is the relaxation time, and A is the area of cross-section of the conductor. From this formula, it is clearly seen that resistance and relaxation time are inversely proportional. And therefore, overall, I can say that for a metallic conductor, resistance increases with increase in temperature. The quantity m upon Ne square tau is the resistivity of the material, and thus rho is equal to m upon Ne square tau is another way of writing the resistivity of a conductor. So overall, I have said that resistance of a metallic conductor increases with an increase in temperature. Now, if this range of increase in temperature is not very large, then I can actually relate the new resistance and the old resistance of a metallic conductor from the formula RT is equal to R0 1 plus alpha T. Keep in mind that this is valid only for a limited range of temperature. So here I see that RT, which is the resistance of the conductor at temperature T, is related to the resistance of the conductor at 0 degrees. Here alpha is known as the temperature coefficient of resistance. From this formula, I get the formula for alpha, that is the temperature coefficient of resistance, which is the increase in resistance per unit original resistance per degree rise in temperature. From this, I can also write down the values of alpha for different types of materials. In metals, alpha is positive. In insulators and semiconductors, alpha is negative. And in alloys, alpha is small as compared to that in metals. Now, I also want to know what is the effect of temperature on the resistivity of a material. The resistivity of the material is given by the formula rho is equal to 1 upon sigma, which is equal to m upon Ne square tau. This formula we just saw a few slides earlier. Sigma here is the conductivity, and we know that resistivity is the reciprocal of conductivity. Now from this it is very clear that the resistivity depends inversely on the number of free electrons per unit volume, which is N, and it depends inversely on the relaxation time tau between collisions of all the electrons, which means that a change in N or a change in tau will result in a change in rho. But we know that when temperature increases, the average time of collision decreases. So tau is actually decreasing with an increase in temperature. Also, in a metal, N does not depend on temperature, and therefore the only thing that is changing rho will be tau. And because tau is decreasing with an increase in temperature, this increases the resistivity of the material. And so I can say that in a metal, rho increases with increase in temperature. In semiconductors and insulators, on the other hand, N also depends on temperature. And therefore we see that N is increasing with temperature in an insulator or a semiconductor. But tau we know is decreasing with temperature. But the increase in N is so much that it compensates for the decrease in tau, and therefore overall the resistivity rho of an insulator or semiconductor decreases with temperature. This is the temperature dependence of the resistivity of a material. We now move on to the most important component of an electronic circuit, and that is a cell. A cell is nothing but a simple device which we use to maintain steady current in an electric circuit. The cell, known as an electrolytic cell, is something we have learned in the lower classes. Its construction is very simple. It consists of an electrolytic solution inside which are dipped electrodes, and these electrodes exchange charges with the electrolytic solution. And this cell overall then provides the energy to the charges of the circuit to complete their movement around the circuit. We already know that this cell, when connected inside a circuit, causes current to flow in the circuit. This entire assembly of the electrolytic solution plus the electrodes consists of the electrolytic cell, which we denote by a symbol in our actual circuits. Now we know that in the outer circuit, the current flows from the positive terminal to the negative terminal. We have seen always that current flows from the positive terminal to the negative terminal. But this is actually true only for the outer circuit. Now what do I mean by the outer circuit? I mean the circuit which is not inside the cell, or the part of the circuit which is not between the electrodes. The path of the circuit from the positive terminal to the negative terminal on the outside is known as the outer circuit, and therefore current actually flows from positive terminal to negative terminal only in the outer circuit through the external resistance R of the circuit. However, in the inner circuit, the current actually flows from the negative terminal to the positive terminal of the cell, and it flows through the electrolytic solution. And this we call as the inner circuit. So we say that on the outside current flows from positive to negative terminal, but in the inner circuit it flows from the negative to the positive terminal through the electrolytic solution. Now we can understand what is known by the electromotive force. If I remove the outer circuit, I am left only with the cell and its electrodes. If I place a potentiometer between these two electrodes and find the potential difference between them when there is no outer circuit, that is, when the circuit is open, and that means external resistance is infinite, then this potential difference is known as the electromotive force. So by definition, EMF, or the electromotive force, is the potential difference between the positive and the negative terminal when there is no current, that is, when the circuit is open, or when we can say the external resistance is infinite. This is denoted by capital E. However, it is important to note that even though the name of E is an electromotive force, it is not actually a force but a potential difference. And this is important to avoid confusion. Now, let me bring back the external circuit. And I say that the potential difference between the same two terminals, that is the positive terminal and the negative terminal, is again measured. But this time it is measured when there is an external circuit. That means it is measured when current is flowing. and therefore the external resistance R is finite because current is flowing. So I say that the potential difference between the terminals again when the current is flowing, that is when there is a closed circuit or when R is finite, is known as the terminal voltage or potential difference. It is also sometimes known as the external voltage because it is the voltage of the external circuit. Finally, I also want to point out that when the charge is moving from the negative terminal to the positive terminal inside the cell, it has to go through the electrolytic solution. And this electrolytic solution will not let it pass without any resistance. And therefore, this solution itself offers a small amount of resistance, which we denote with the letter small r. And this is known as the internal resistance of the cell. This resistance is due to the electrolytic solution itself. Now let's try to find out the relationship between the internal resistance denoted by small r, the capital R, that is the external resistance, the electromotive force, and the terminal voltage. To understand this, remember that whenever a charge leaves the battery or the cell, it leaves with some amount of energy. It leaves with it a voltage equal to E, and it uses this voltage to cover its path all around the circuit. And this path includes not just the external circuit which we can see, but it also includes the internal circuit through the cell. So whenever a charge leaves a battery, it leaves with a voltage which it uses to cover the entire path of the circuit, which includes the outer plus the inner circuit. Now let's see what happens when this charge is moving through the circuit and how its energy or voltage is being spent. Starting with the voltage E from the positive terminal, as the charge begins to move through the external circuit, its voltage is decreasing. When it reaches the negative terminal, that is when it finishes the external circuit, its voltage has now reduced. So how much voltage has been used to go around the external circuit only? This voltage, which is used only by the charge to go in the outer circuit or the external circuit or the circuit between the positive and the negative terminal on the outside, this voltage is the terminal voltage given by capital V. What will it do with this remaining amount of voltage or energy? Because the battery gave it E amount and it has only finished V amount. So what will it do with the remaining energy that it has? With the remaining energy that it has, it will go through the cell from the negative to the positive terminal and thus finish its circuit. And therefore, as you can see, through the cell, it will have to overcome the internal resistance. And from Ohm's law, I can write down what is the voltage drop when it goes through this internal resistance, and it will be IR, where I is the current of the circuit and R is the internal resistance. From this, it is very clear that the total voltage E which it received from the battery is equal to capital V which it spent in the external circuit plus IR which it is spending in the internal circuit. And so I get the relationship between EV and small r, that is E is equal to V plus IR. And this relationship is extremely important. From this relationship, I can actually find out another equation. In this equation, instead of writing capital V for the external voltage, I can use Ohm's law and write capital V as I into R, where R here now is the external resistance. Replacing this in our relationship, we get E is equal to capital IR plus I into small r, and from here I get the value of current, that is capital E upon capital R plus small r. And this is obvious because current is nothing but voltage upon resistance, and E is the total voltage, and therefore you divide it by the total resistance, that is internal plus external. So this gave me the value of the current in a circuit where I have also considered the inner and the outer circuit. Now finally, it's a very important thing to note that if you want maximum current in a circuit, you have to reduce your external resistance, because you cannot do anything about the internal resistance of a cell, and therefore the maximum current that can be passed through a circuit can be passed when the external resistance is 0. And if external resistance, that is capital R, is 0, then we'll get the maximum value of current, that is I max, which will come out to be capital E divided by small r only. Just like resistors, cells can also be combined in different combinations so that we can manipulate the voltages of a circuit. The first type of combination of cells that is possible is a series combination. In a series combination, we take two cells in which one terminal of both of them is joined together such that the other end of both the cells is free. When doing this with resistors, it's quite simple. However, when we do this for cells, two cases emerge. In the first case, if we have two cells, that is E1 and E2, each having internal resistance R1 and R2, you can see that one way to join them in a series combination is by connecting the negative of the first to the positive of the second. However, there is also going to be another case. In case 2, again I have these two cells E1 and E2, but this time the other way to join them in a series combination would be by connecting the negative or the positive of first to the negative or positive of the second. That is, this time I connect the same polarities together. Therefore, in this case, I see that the negative is connected to the negative, and this will give rise to case 2 of the series combination. In both these cases, the goal is to find the equivalent EMF of the circuit and the equivalent internal resistance. So basically, I'm asking the question, what would happen to the total EMF of the circuit if I take two cells of EMF E1 and E2 and connect them in series? So let's take a look at these cases one by one. In case 1, as you can see, I have connected the negative terminal of the first cell to the positive terminal of the second cell and thus created a series combination. If I take a look at this case, I will find that E1 and E2, which are the EMFs of the two cells, and R1 and R2, which are the internal resistances respectively, can be used to find the equivalent EMF and resistance of the circuit. Thus, I get the formula for the equivalent EMF, that is, if two cells are connected in series in such a way that the negative of the first is connected to the positive of the second, their EMFs simply add up. And therefore, the total combination EMF is E1 plus E2. On the other hand, their internal resistances also add up. So what I'm saying is basically this. If you are given a number of cells which are connected in series in such a way that opposite polarities are all connected to each other, then simply add up all their EMFs and their internal resistances. However, I can also do the second case. In the second case, now as you can see, I have connected the negative electrode of the first cell to the negative electrode of the second cell. In this second type of combination again, I will write down the equation which gives me the equivalent EMF of the circuit and the equivalent resistance of the circuit. In such a case, it turns out that the equivalent EMF is E1 minus E2, whereas the internal resistance still gets added up. Therefore, for case 2, it turns out that the EMF of the total combination is equal to E1 minus E2, and the internal resistance of the total combination is simply an addition of the individual internal resistances, that is R1 and R2. So what do we conclude from this? The first conclusion that we can make from these two cases is that the equivalent EMF of a series combination of any number of cells is just the sum of their individual EMFs. However, this is valid when the current is leaving each cell from the positive electrode, which is what happened in case 1. So whenever the current leaves each cell from the positive electrode, in such a case, you simply add up the EMFs. However, if you have a case in the combination where there is a cell in which the current is leaving from the negative electrode, then for that cell and for that cell only, you will write the EMF with a negative sign. This is what happened in case 2. In case 2, the EMF of the second cell was written with a negative sign. That is why we had a minus E2 in the formula. And we did this because in this case, the current was leaving from the negative electrode. And therefore, overall, whenever you combine cells, you must look at where is the current leaving from. If it leaves from the positive electrode, then you write it with a plus. If it leaves from the negative electrode of the cell, then the EMF of that cell is written with a minus sign. However, in case of the internal resistances, the total resistance, internal resistance of the whole circuit is just a combination or an addition of all the individual internal resistances in both the cases. Now we can also see that there is another type of combination in which we can connect the cells in a parallel combination. In such a case, a parallel combination of the cells involves joining the two electrodes of both the cells. Here, as you can see, E1 and E2 with their individual internal resistances R1 and R2 are joined from both the terminals. This is a parallel combination. Now we want to find out the equivalent EMF and internal resistance of such a combination. That is, what is happening to the total EMF of the circuit if I take two cells and join them parallelly. In such a case where we have a parallel combination between two cells E1 and E2, we will see that the current is flowing through the circuit as shown in the figure. In this case, the equivalent internal resistance is given from the formula 1 upon Req is equal to 1 upon R1 plus 1 upon R2. So I can see that the reciprocal of the total equivalent resistance is the sum of the reciprocal of the individual resistances. Using this formula, we find the equivalent EMF of the circuit, and it is given as EEQ divided by REQ is equal to E1 by R1 plus E2 by R2, and these are the formulae which help us find the equivalent EMF and internal resistance in a parallel combination of cells. Let's now take an example to understand if we have really analyzed the situations of the series and parallel combination perfectly. Here we have a mixed combination of cells. As you can see, I have a total of 12 cells in the circuit. This is a mixed combination because there are 4 cells in each row which are connected in series. However, these 3 rows are connected in parallel with each other. The number of cells in each single row is given by the letter N, and here N is equal to 4. However, the number of rows which are connected in parallel is given by the letter M, and here M is equal to 3. Now I will use the series and parallel formulae to find the equivalent EMF and internal resistance of this circuit. Remember, the total number of cells in this circuit is equal to 3 into 4, or I can say it is equal to M into N, and it is given by 12. Let's first tackle the series combination of each row. In each row, there are 4 cells, each of which have the same EMF equal to E. I will apply the series formula, that is, I simply add these EMFs and I get the equivalent EMF of the first row as 4E. I can also simply add their internal resistances as we have seen, and I get the equivalent internal resistance of the first row as 4R. Now I can replace all the 4 cells of the first row by a single cell whose EMF is 4E and internal resistance is 4R. I can do the same for the second row and the third row as well, because they also have a 4-cell combination in series. Now what I am left with is simply 3 cells in parallel. Now I will use the parallel cell combination, and using this I will get that the equivalent EMF is simply 4E, because in a parallel combination where each of them have the same EMF, you will find that the formula leaves you with the same EMF as the individual EMFs. So the equivalent EMF in this case is 4E. However, the internal resistances come out to be 4R upon 3. Now from here I want to make a final point. If you take a careful look at what we have found that the final and equivalent EMF of that big circuit of 12 cells comes out to be 4E, and the final internal resistance of that big circuit comes out to be 4R by 3. From this I can understand that in general, if I had a circuit of N cells in each row, then I would get an equivalent EMF of NE. Remember, N is simply the number of cells in each row. How was I able to write this general equation? I know because here in the case that I just analyzed, the answer came out to be 4E, and 4 was nothing but the number of cells in each row. So I generalized this formula and I wrote it as NE. If there are N cells in the row, then the equivalent EMF will be NE. Similarly, I will look at the second formula, that is equivalent resistance comes out to be 4R by E, which is nothing but NR by M, because 4 was the number of cells in each row and 3 was the number of rows in parallel. So if I want to generalize this equation, I will generalize it to NR by M. So again, remember, the equivalent EMF is found by writing NE and the equivalent internal resistance is found by writing NR by M. Finally, the current from each cell in such a circuit comes out to be I upon N, where N is the number of cells in each row. Now, the next thing that I want to talk about is electrical energy. Now, we know that current always flows from a point at higher potential to a point at lower potential. And if the potential at the higher point, let's say point A is VA, and the potential at the lower point, let's say point B is VB, then the change in potential between A and B is written as VA minus VB, and that is equal to V. And since it's flowing from a higher potential to a lower potential, this V is always greater than 0. Now, what does this mean? This means that the potential energy in a circuit as the current flows is always decreasing. Now, we know from the work energy theorem that whenever potential energy decreases, there should be a gain in the kinetic energy. In case of a circuit, if I consider that no collisions are occurring, it means that this loss of potential energy will result in a gain in kinetic energy of the charges, which means that delta K will be greater than 0. But do we really get to see this kinetic energy in action? We don't, because we know that if delta K was greater than 0 and all the electrons were always gaining kinetic energy, then their speeds should go on increasing. But this does not happen, because in reality we cannot neglect the collisions that occur. And because of these collisions, this kinetic energy does not increase the speed of the electrons, but instead gets dissipated or converted into heat. And we know this because things that current is passing from, if you touch these things like a wire, you can feel the heat that is dissipating from such objects. And therefore we say that the energy, that is the kinetic energy, is converted into ohmic loss or loss due to heat. This delta W, that is the work done, which we found as delta K, is the heat that is lost through a wire, and we can write this also as IV into delta T. Finally, now I can take the delta T on the other side and get the formula for power. And the formula for power is delta W upon delta T, which is equal to IV. So therefore, we've got the formula for electrical power. I can also write this using another formula. Instead of this V, I can write it as IR from Ohm's law, and therefore this will become P is equal to I square R. This is another formula for power. We can also write this as V square by R. So we have three formulas for power. You can write it as IV, you can write it as I square R, and you can also write it as V square by R. But the main question is that this power dissipated that we have just calculated is actually going out as heat, and this is what is known as ohmic loss. Ohmic loss is nothing but the power dissipated in an electrical circuit which goes as heat and therefore heats up the circuit. Now the final question that I want to ask is, where is all this power even coming from? Now this power has to come from somewhere because an external source is required to maintain a steady current in the conductor. This external source is therefore supplying the power that we are talking about. In case of an electrolytic cell, it is the chemical energy in the cell that supplies the power. Finally, if we take a look at the formula once again, we'll see that P is equal to VI, which is equal to I square R, which is equal to V square by R. And simply speaking, we can say that power actually depends upon the resistance and the voltage. And therefore, by changing the resistance or the voltage of a circuit, you can manipulate the power transmitted through a device. An important application of the concept of electrical power is its use in power transmission. Now we know that electrical power comes to our homes from power stations which are really far away. And this power is brought to our home through transmission cables. And we just saw that whenever electricity passes through an electronic instrument or even a wire or a transmission cable, there will be a dissipation of heat. And therefore there will be some power loss, which we saw was ohmic loss. Now obviously we want to minimize this power loss when the power is being transmitted from the power station to our homes. And therefore to minimize the power loss in the transmission cables, let us see what we can do. Suppose that we want to deliver power to some device inside our homes. And let's say that this power is coming through the transmission cables and these transmission cables have some resistance. Now suppose that the voltage across the device inside my home is V and the current which passes through this device is I, then I know that the power required to run this device successfully is equal to VI, which means that my transmission cables should bring VI from really far away. And therefore P is equal to VI. However, let's see what will be the power loss when this power is being delivered by the transmission cables. Now, transmission cables will also have some finite resistance. Let's say that the transmission cables have some resistance equal to RC. Now, if they have a resistance equal to RC and they have a current equal to I, why is it I? Because it's the same transmission cables that are delivering the current to your device, and therefore the current passing through the device in your home and through the transmission cables will be exactly the same, and therefore I can write that the power dissipated in the connecting wires, which is wasted, is I square RC, where I is the current passing through them and RC is the resistance of the transmission cable. From here I get that the power loss is I square RC. However, we know that the power delivered to the device is going to be VI, and from there I can substitute the value of I and write it as P by V, and therefore I'll get that PC is equal to P square RC by V square. Now it's very clearly easy to see that to reduce this PC, which is the power loss, these wires have to carry current at large values of voltage, and this is achieved during the transmission using transformers. However, you don't only have to increase the voltage, but you also have to decrease it. This is because when the power reaches our homes, such high values of voltages are not safe for use, and therefore at the other end, when the voltage is reaching our home, it needs to be stepped down using another transformer. So you can see that we have learned three things. First, to minimize power loss, the power needs to be transmitted at high voltages. However, to do this, we'll need a step-up transformer. And finally, when the power has to be reached to our homes, these high voltages are very unsafe, and therefore we need another transformer to bring down the voltage so that it is safe for use. So let's quickly take a look at how power is transmitted from a power station to our homes using all these 3 points. So as we have already seen, there are 3 stages to power transmission. The power has to go from the power station through the transmission cables and has to reach our homes. So let's see what is the journey undertaken by this power as it leaves the power station. The power generated at the power station must first be stepped up using a step-up transformer. This is done because power transmitted at high voltages has minimal power loss, as we have seen. This power is then transmitted using transmission cables. However, when this power reaches close to our homes, we need to bring down the voltages again in order to ensure safe use. And therefore, the next stage in this journey is the step-down transformer, which brings down the voltages of the power. Finally, this power, which is now safe to use, is delivered to our homes, allowing us to use the electrical appliances that we use in our daily lives. This is the journey of electrical power from the power stations to our homes. Now, electric circuits made up of a combination of cells and resistances can get very complicated very fast. And in such a case, the formulae that we have learned about series and parallel resistances in cells may not be sufficient to analyze these circuits successfully. And therefore comes in handy these 2 laws known as Kirchhoff's laws, which are extremely useful in analyzing electric circuits. So let's see what these laws are. The first thing that I want to do is give you a general instruction on how to label the devices in your circuit in order to successfully use Kirchhoff's law. So let's look at some labeling instructions. The first instruction is that you must label the current in each resistor and use a directed arrow to indicate that direction of current along the resistor. So basically, you have to indicate the direction of current in every single device that is inside your circuit. Now, you might ask the question, how do I already know what is the direction of the current without even analyzing the circuit? And the answer to this is that you don't. You just make an educated guess. And how will you make this educated guess? You'll make it through practice. But then what happens if your educated guess is wrong? That's absolutely fine, because the second instruction says that if ultimately I, that is the current that you have marked, comes out to be positive through our calculations, it means that the current that you had marked is correct and that direction is the right one. However, if in the end of our calculations, the value of I comes out to be negative, then it means that the direction of the current assumed by us was wrong and the actual current is flowing in a direction opposite to that arrow. So this is very simple. Take a direction in each single resistor and then solve the sum. And if it's wrong, that is, if it comes out to be negative, then you have to understand that the current had to be opposite to what you have assumed. The next instruction says that for each source, for example, a battery, a cell, or any other combination of batteries, for each source, the positive and negative electrodes must be indicated. So you must write plus for the positive electrode and negative for the negative electrode. You also have to mark an arrow along the cell to show what direction the current is flowing through the cell. And you have to make sure that the same current enters and leaves a cell. So what did we learn? We learned that for every source, we must mark the positive and negative electrodes, and we must mark the current flowing through the source and make sure that the same current enters and leaves the cell. Now, one very important thing to remember is that we learned some time back that through the cell, the current always flows from the negative terminal to the positive terminal. And therefore, the current when you mark through the cell will be from the negative terminal to the positive terminal. And in such a case, the formula that will come in handy will be V is equal to E minus IR, where V will be the voltage drop across the cell, E is the electromotive force, I is the current, and R is the internal resistance. But what happens if you mark the current flowing from the positive to the negative terminal? If you mark it instead of going from the positive to the negative terminal, then remember you'll have to change your formula accordingly. You'll have to make it V is equal to E plus IR. Therefore, I say that if while labeling the current through the cell, if you pass it from the positive to the negative, then the formula is V is equal to E plus IR. Now that we have learned the labeling instructions, let's take a look at the first Kirchhoff law. The first Kirchhoff's law is also known as the Kirchhoff's current loop or the junction rule. Now, what exactly is the word junction? The word junction means a point on the circuit where multiple currents are either coming in or going out. So any point where two or more than two currents are meeting, that is either they are coming into the point or going out of the point, such a point is known as a junction. In such a case, if you want to analyze the currents, we use Kirchhoff's current law or the KCL or the junction rule. So let's take a look at what is happening in this example. As you can see, point O is clearly a junction where four currents are either coming or going, and therefore now we can use the junction rule, and the junction rule says that at any junction the sum of the currents entering the junction is equal to the sum of the currents leaving the junction. And this is actually pretty simple. It means that the total sum of currents must be 0. But how are you going to get 0 only by addition? If I apply this KCL rule to the junction O, as you can see in the figure, then it's very clear that I2 plus I4 is the current that is coming inside the junction, and I will write that with a positive sign, whereas I1 and I3 are currents going out of the junction, and I write that with negative signs, and I get that I2 plus I4 minus I3 minus I1 is equal to 0, because we said that the sum of the currents entering is equal to the sum of the currents leaving, or we can say that the total sum is equal to 0, and from here I get that I2 plus I4 is equal to I3 plus I1. And this is how we have applied the junction rule to this circuit. Now the second law is the Kirchhoff's voltage law, and this one is slightly trickier. And therefore, before we apply Kirchhoff's voltage law, let's try to remember what we can do to use this rule successfully. Kirchhoff's voltage law basically says that in any closed part or loop of an electrical circuit, the algebraic sum of the EMFs, which are the sources of power in the circuit, is equal to the algebraic sum of the product of the resistances and currents flowing through them. So this seems a little bit complicated. Just remember that there are two things. One are the sources, which are your EMFs or the cells, and the other are your resistors, or basically anything that is using the power in a circuit. So all that it is saying is that the sum of the potential difference of the EMFs is equal to the sum of the potential difference or the voltage drops across all the devices which are using the power. And this actually seems pretty obvious. Whatever the power is given to the circuit should be equal to the power used in the circuit. So I'm saying that the total voltage of the sources is equal to the total voltage of the devices which are using this voltage. Okay, so let's see. I write this mathematically as the sum of the EMFs, that is sigma E, is equal to the sum of the product of current and resistances. And product of current and resistance is nothing but the voltage drop. And therefore, I can say that sigma E is equal to the sigma IR. Now, this is, like I said, nothing but pretty obvious, because you see, the potential of a point depends only on the location of a point. So if I'm going in a loop, that means I'm starting from one point and coming back to the same point, and therefore I should not have any change in potential. And if I don't have any change in potential, then the voltage drop across the loop should be zero. And thus it is nothing but a statement on the conservation of energy. It is basically analogous with the conservation of energy, because it is moving around a closed loop. You will end up back to the same point where you started, and if you end up at the initial point, then there should be no loss of voltage. You can't go from one point, come back to the same point, and suddenly see that the voltage has changed. It should be exactly the same, and therefore there will be no loss in the voltage when moving around a closed loop. So now let's see if we can use Kirchhoff's voltage law. Now, two very important rules have to be remembered while using Kirchhoff's voltage law. The first one is that you can traverse or go around the loop in any direction you want. However, when you do so for a cell, remember that if you're going from the negative terminal to the positive terminal, the voltage is positive. However, in case of a resistor, if you are going through the loop and you come across a resistor and you are traveling or passing the resistor in the same direction as the current, then the voltage is taken to be negative. So remember, if the direction of the current and the direction in which you are going is exactly the same for a resistor, then the voltage is going to be taken to be negative. Now, this might sound confusing. Let's see a small demonstration. Let's take a look at this circuit. In this circuit, it's very obvious that there are three full loops. The first one is the one where there is an EMF of 10 volts and there is a resistance R1 across which there is a voltage drop of V1. The second one is the loop DEF. In this, there is again an EMF of 5 volts and two resistors R1 and R3, each of which have a potential drop of V1 and V3 respectively. Finally, we have the third loop. This loop is CFE. I have another EMF of 7 volts and again I have two resistors in this loop as well. If I take a look at the first loop and I choose to travel this loop in the clockwise direction, I will see that the first thing that I'm coming across is the EMF. Now remember, since I'm going in the clockwise direction, I'm actually going to go through this EMF from the negative terminal to the positive terminal, and therefore according to the rule, this voltage will be taken as positive, and therefore I write down that AB is plus 10. The next thing that I'm going to encounter while going through this loop is the resistor R1. And when I go through the resistor R1, you will see that I am going through the resistor from C to D, and the current is also passing through the resistor from C to D. So the resistor's current is in one direction and the way I am going through the resistor is also in the same direction, and therefore this voltage will be counted as negative, and therefore I say that CD is minus V1. And now apply Kirchhoff's voltage law, which basically says that all the voltage across the power and all the voltage across the resistor should be equal, and therefore I say that 10 minus V1 is equal to 0, because the sum of all the potential differences in a circuit in a closed loop should be 0, and therefore I see plus 10 minus V1 is equal to 0. This gives me the value of V1, which is equal to plus 10. Now I move on to the second loop. In the second loop, as you can see, again I have DCE and you have two resistors and one EMF. Now again I'm going to go around this loop in the clockwise direction, and when I do so, you will see that the first thing I encounter is the resistance R1. Now remember, I am going through this loop in the clockwise direction, which means I am going through this resistor R1 from D to C. However, the current in this resistor is flowing from C to D, and therefore the voltage across this resistor is going to be taken as positive, because the direction in which I am traversing it and the direction in which the current is flowing is opposite, and therefore I will take the voltage across the resistor to be positive. As I go along the loop, the second thing that I encounter is the resistance R3. As you can clearly see, I am going through this resistor from C to E. However, the current through this resistor is flowing from E to C, and therefore because they are in the opposite directions, the voltage across this resistor will also be taken to be positive, and therefore I see that CE is equal to plus V3. Finally, the third element in my loop is the EMF, and as you can see, I am going to go through this EMF from the positive terminal to the negative terminal, and therefore I must assume this EMF is negative, and I write ED is equal to minus 5V. Now I apply Kirchhoff's voltage law, which is saying that the sum of the total voltages in a closed loop is 0, and therefore I see that I get V1 plus V3 minus 5 is equal to 0, but I know V1 is 10, and therefore I get V1 plus V3 is equal to 5. Then I substitute what is V1, that is 10, and I get V3 is equal to 5 minus 10, which is equal to minus 5 volts, and thus I have got the voltage of V3 as well. So this is one small demonstration to show you how we can use Kirchhoff's voltage law to analyze a closed loop. Now let's look at an application of Kirchhoff's rules. The first and very important application is the Wheatstone's bridge. Wheatstone's bridge is nothing but a network of 4 resistors. That is, the resistors R1, R2, R3 and R4 are connected in a diamond shape arrangement, and this arrangement, when you will actually connect it in your labs, will look something like the other figure where you have actual resistors replacing the symbols of the resistors. Let's see how these two circuits are exactly the same. The first resistor AD, as you can see, that is a resistor R1, is pointed out for you in the actual circuit, and similarly you have R2, R3, R4. So you can see these 4 resistors make a simple circuit. When you actually connect them in the lab, they will not look like this diamond when you're doing this in your laboratory. You can also see that a battery is connected between the points A and C, and therefore AC is known as the battery arm, and you can see that a galvanometer, that is a current measuring device, is connected between the points B and D, and therefore BD is known as the galvanometer arm. The cell is assumed to have no internal resistance. Now let's see what happens in the circuit. Now in general, the current which will start from the cell will flow through the circuit, that is the Wheatstone's bridge. There will be a current in all the different arms of the bridge. However, what we are interested in is the balance condition of the Wheatstone bridge. The balance condition is that condition for which there is no current flowing through the galvanometer, and therefore it is the condition where the current through the galvanometer is 0, and the balance condition for a Wheatstone bridge is simply given by the following formula. It is R2 upon R1 is equal to R4 upon R3, and this is known as the balance condition of a meter bridge. The condition for a meter bridge remains unchanged on mutual interchange of the positions of the cell and galvanometer in the circuit, which means that if I remove the galvanometer from between points B and D and I move it to the points A and C, and I remove the cell from A and C and I switch to B and D, that means I have simply interchanged the positions of the cell and the galvanometer. In doing so, you have changed nothing, and the condition for the balanced bridge will not change. So interchanging the cell and the galvanometer arm will not change the balance condition of a Wheatstone bridge. Finally, remember that a Wheatstone bridge has maximum sensitivity for that situation where all its resistances are the same. So as you can see, instead of writing R1, R2, R3 and R4, I have written R, 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 and this is the condition of maximum sensitivity of a Wheatstone bridge. An important variation of the Wheatstone's bridge is the meter bridge. As you can see on the diagram on the left, this is the representation of a meter bridge. On the right hand side, you have the Wheatstone bridge as we know it, and let's quickly see how these two are the same circuit. You can see that instead of a resistance R2, I have the resistance S between the points A and B. Similarly, instead of R4, I have a resistance R between the points B and C. And instead of the resistance R3, I have a length of a wire connected between C and D. And similarly, I also have a wire connected between A and D. So you can see that we know that wire also has resistance, and therefore here instead of resistance I am using the resistance of the wire as a resistance in the arm AD and CD. Now the entire length of the wire AC is taken to be 1 meter or 100 centimeter. One end of the galvanometer is connected to the point B and the other end of the galvanometer is connected to a jockey. A jockey is nothing but a metallic rod with a knife edge at one end, which slides over the wire to make electrical contact. Now the resistances S and R are connected in the left and right gaps of the meter bridge. R is the unknown resistance. The resistances P and Q, which are the two other resistances of a Wheatstone bridge, are considered with respect to the balancing point D such that we get their resistance by looking at the length of the wire between the points. For example, the resistance P will be determined by finding the length of the wire AD. Similarly, the resistance between C and D is directly proportional to the length of the wire DC. Our goal will be to find the point D. Let's take a look at an application of the meter bridge. The first application is to find an unknown resistance. In this case, when you assemble the circuit for a meter bridge in the lab, you will see the following equipments. Initially, you will connect the meter bridge point A to the positive terminal of the cell. The negative terminal of the cell will be connected to point C on the meter bridge. A resistance S, which is the standard known resistance, will be connected between one gap, that is the left gap of the meter bridge, and the other resistance R will be connected between the other gap of the meter bridge. A galvanometer will be connected between the point B of the meter bridge and the jockey. As you can see, the resistance R is the unknown resistance, which is nothing but a piece of a wire whose resistance we want to find. The resistance box represents the standard known resistance. Our goal will be to find the unknown resistance R. In order to do this, we move the jockey on the meter bridge. As we slide the jockey, we must find the point on the meter bridge at which the deflection in the galvanometer comes down to 0. Let the distance of the jockey from the end A at the balance point be L. In such a case, the portion AD of the wire has a resistance RCM into L, where RCM is the resistance of the wire per unit centimeter. The length of the portion DC will then be 100 minus L, and the resistance of this portion will be RCM into 100 minus L. Once we find the balance point D, we write down the values of L and 100 minus L, and then we can use the condition for the balanced bridge. That is, S upon R is equal to RCM L upon RCM 100 minus L. Since RCM cancels from the numerator and denominator, this leaves us with L upon 100 minus L. And thus, we don't even need to know the resistance per unit centimeter of the wire. We can simply use the condition that S upon R is equal to L upon 100 minus L to find the unknown resistance R in our experiment. The second application of the meter bridge is to find the unknown resistance of a galvanometer. This is also known as Kelvin's method. The only difference in the previous circuit and this circuit is, as you can see, between the points B and D, where initially there was a galvanometer, now is a simple wire. Similarly, in the left gap, initially there was a resistance S, and now there is the galvanometer connected between the left gap. In this case, the experiment does not involve finding the null deflection point. Instead, we first look at the deflection of the galvanometer before connecting the jockey to any point on the meter bridge. After that, we move the jockey on the meter bridge in such a way that D is a point where galvanometer shows the same deflection after connecting the jockey as it did when the jockey was not connected. Once we find this point, the same logic applies. In the balanced position of the bridge, G upon R will be equal to L upon 100 minus L, and this will give us the value of the galvanometer's unknown resistance. The value of this resistance will be given by the formula G is equal to L upon 100 minus L into R. The potentiometer is based on the principle that the fall of potential across any portion of a wire is directly proportional to the length of that portion, provided the wire is of uniform area of cross-section and a constant current is flowing through it. We use this principle even in case of the meter bridge. Basically, we're saying that the voltage drop across any length of the wire is directly proportional to its length. And therefore, if I try to remove the proportionality, then I will have to introduce a constant. In this formula, V is the potential drop across the portion of the wire, L is the length of the portion of that wire, and X, which is the constant of proportionality, is nothing but the potential gradient, that is the fall of potential per unit length of the wire. Once we know this principle, the understanding of potentiometer is comparatively extremely easy. A potentiometer is based on the balance condition that when no current flows through the galvanometer, that is, when sliding the jockey, if you see no current on the galvanometer, that means V is equal to E and the potentiometer is balanced. Let's first take a look at the primary circuit of the potentiometer. Now, a potentiometer is basically just a long piece of uniform wire. This wire may be a few meters in length, across which a cell is connected. Sometimes the wire is cut in several pieces, as you can see. The actual picture of the potentiometer, that is of this wire, is as shown on the table. This wire is cut into several pieces and placed side by side and connected at the ends by thick metal strip and looks something like that shown on the table. The figure that you see in the box is the primary circuit of a potentiometer. And on the table are the actual instruments which we will now demonstrate how to connect to make the primary circuit. This is known as the primary circuit because all the applications that we will now learn will only be additions to this circuit. As you can see, the first connection made is between the positive terminal of the battery and point A on the potentiometer. A and B are connected and point B is connected to one end of the rheostat. The other variable end of the rheostat is connected to a one-way key and the other end of the one-way key is connected to the negative terminal of the battery. This completes the primary circuit. Now let's start using the potentiometer. The first application is to be able to compare the EMFs of any two cells. In order to do this, we will use first the individual cell method. The individual cell method involves adding some connections to the primary circuit. The first connection is that from point A, a wire is connected to the positive terminal of the first cell whose EMF has to be compared, and the negative terminal of that cell is connected to the first terminal of the three-way key. Similarly, point A is connected to the positive terminal of the second cell and the negative terminal of this cell is connected to point 2 of the three-way key. The third terminal of the three-way key is connected to one end of the galvanometer and the other end of the galvanometer is connected to the jockey. Now we are ready to use the individual cell method in order to compare the EMFs of the two cells. The way the three-way key works is that you place the key in any one of the connections, that is, here we have placed it between 1 and 3. In such a case, the connection between 2 and 3 is open. So it helps us connect one circuit at a time. In order to perform the experiment, we place the key between 1 and 3 and slide the jockey till the galvanometer shows null deflection. This point marked as N1 and the length AN1 is the first length that we require. Similarly then, the key is removed from between 1 and 3 and placed between 2 and 3 and now the jockey is slid again and now we get the second null point deflection point, that is N2. The balance condition is then given as E1 upon E2, which are the EMFs of the two cells which we want to compare, is equal to the length L1, that is the length between point A and the first null deflection point, and L2, which is the length between A and the second null deflection point. By measuring L1 and L2, we can compare or find the ratio between the EMFs of the two cells. The second method is the sum and difference method. The only difference in this method and the previous one is that instead of connecting one cell at a time, we connect combinations of cells in the two branches. In the first branch, we take the two cells and connect them in such a way that the negative of the first cell is connected to the positive terminal of the second cell. In the second case, we do the opposite. Remember, however, these two cells are the same cells as were in the first method. We are trying to compare the EMFs of the same two cells, but we are now using a different method. In this case, we add the following connections to the primary circuit. First, we connect point A to the positive terminal of the first cell. The negative terminal of the first cell is then connected to the positive terminal of the second, and the negative terminal of the second is connected to terminal 1 of the three-way key. Similarly, we connect point A to another identical copy of the first cell, that is to the positive terminal, and connect the negative terminal of the first cell to the negative terminal of the second cell, and the positive terminal of the second cell is connected to terminal 2 of the three-way key. Remember, E1 and E2 are the same cells in the first type of connection and the second type of connection also. Then we connect terminal 3 to one end of the galvanometer and the other end of the galvanometer goes to the jockey. As usual, we place the key in the first between the 1 and 3rd terminal and move the jockey till we get the first null deflection point, that is N1. We repeat the same for the second connection, that is, we remove the key from between 1 and 3 and place it between 2 and 3 and then repeat that is slide the jockey and get the second null deflection point. In this case, the balance condition will be E1 upon E2 is equal to L1 plus L2 upon L1 minus L2, where L1 is the distance between A and the first null deflection point and L2 is the distance between A and the second null deflection point. This is the sum and difference method. Finally, the potentiometer can also be used to measure the internal resistance of a cell. In such a case, the following connections have to be made to the primary circuit. We connect point A to one end of a one-way key and its other end is connected to a standard resistance box. Point A is also connected to the positive terminal of the cell whose internal resistance has to be measured, and the negative terminal of this cell is connected to the galvanometer. The resistance box is also connected to one end of the galvanometer and the other end is connected to the jockey. The jockey is moved to find the null deflection point N1 without putting the key in the one-way key. Therefore, with the open circuit, we find the null deflection point N1. And in the second case, we close the circuit by placing the key and again find the null deflection point, which we will call as N2. The balance condition in this case will be E by V is equal to L1 upon L2, where L1 is the distance between A and N1 and L2 is the deflection between A and N2. In this way, we can find the internal resistance of the cell. By replacing E with IR plus R and V with IR using Ohm's law, the I's will get cancelled and we will get L1 upon L2 is equal to small r plus capital R upon capital R, where capital R is the resistance or the load that you have introduced in the resistance box. So this completes all the concepts that I want to talk about under the current electricity concept. I hope you enjoyed this video. Hi guys, thank you for watching our video, and if you like our channel and you like our videos, please subscribe. You can click on the link here and subscribe to our channel. You can also buy our very own target books which we make with the same enthusiasm by clicking on the link here. Thank you for watching and stay tuned.